Hello everyone, welcome to lecture 6 of this course. In the previous lecture, we have discussed how recursion and if then else can be encoded in the framework of lambda calculus. We have also studied the Y combinator. In today's lecture, we are going to study some other combinators and see how they are related to the Y combinator, and we are also going to study some well known functions and how that can be encoded as a recursive function. These are recursive functions as a lambda term. So, we first study a combinator that was invented by Turing, Alan Turing. So, this is called the Turing combinator. So, Turing combinator, we have seen the Y combinator. Y combinator is Y is equal to lambda f. So, this form is what we want to study, lambda f dot q q. So, this form is lambda f dot q q. Now, Turing combinator is written in big theta. It is not. So, we see whether there is any similarity. If we look at it and compare whether we can find any similarity between these two. So, it is not structurally similar because here we have it is of the form PP. Another first we note it is of the form PP. Same thing is repeated. This is repeated here. So, this is a function of two arguments, but then other than this is a subterm xx, it is also containing xxy. So, xxy is a subterm, not xx. The only thing is that xx is somehow coming. Other than that, they do not have any structural similarity. So, we want to see whether what feature can we say about theta. So, let us try to do theta t. So, if you do theta t, so you have this term, that is pp, this is here, and this is our t. So, if we do beta reduction, so now it is of this form pp, ppr. Now, we know that this is equivalent to ppr. It is not really coming around. So, we have to evaluate pp first. So, this is our p, this is our p. So, we have to do ppr, pp we have to evaluate. pp evaluate means, that means pp evaluation means we have to do lambda x dot lambda y. So, let me write it this only p, because otherwise it will be very difficult to read. So, we written it like this. So, here x will be, I will not cut it again, that will be like this. So, in this body x will be replaced by p. So, we get lambda y dot y, then what we have, now we have p, now we have p, now we have y. This is what we have. pp, again we have pp. pp is what we have. Now, our original term, remember our original term is pp. So, we can write lambda y dot y. So, we can write it as big theta y. This part is our, so we are doing pp. This is our pp. pp we have obtained this part, lambda y dot y big theta y. Then what about our theta t? Theta t will be ppr. That means now we have to do lambda y dot y, theta y, and here we have to do t. Now beta reduction will give us t, big theta t. So, this is like yt is equal to tyt. So, the behavior then of the Turing combinator and Y combinator, they are quite similar, although they look very different, but we have obtained that Turing combinator theta t is the same as. So, you see whether can we go through the proof once again. Here first point to be noted, BPR is not, it is not P, it is M and P. So, left associativity, so it is PPR. So, that is why we did PP. When we did PP, we got PR. Now, PP we know, this is, we can substitute, this is our theta. So, we have substituted it here, then we did theta t. So, we have done. So, YT is equal to TYT or theta t, or we can replace y by theta. The Turing combinator has t theta t. So, this is another combinator. So, we have obtained two combinators, y and t. Now, let us see, we have seen Y combinator, and now we want to see whether, so the idea was Y combinator is designed to work in a call by name setting. Call by name setting means if I have a term like lambda x dot m and n, then all free occurrences of x in n is replaced with n. N is not done, nothing, we are not going to touch n, it will be remaining as it is. So, then that is the argument of this function we are not evaluating. it is the name, that is the n, is going to be replaced with where x is occurring free in M. Unlike this, call by value says that this argument n will be evaluated first before it is applied to the function lambda x dot m. Now we want to see whether this, what will happen if y is used in a call by value setting. This is what is of our interest. So then if we do this, so we will do yf. So yf beta reduction, we are going to get beta reduction. So that means f will be replaced. So we are going to get lambda x dot f x x, and we are going to get lambda x dot f x x. This we have done. This is a beta reduction. Now as per the CBN, what we have done, f is replaced here and we have done, this is beta reduction. Now this is of this form, it is m and this is n. This is m, this part is again m1 m prime and this is n here. Now here again we will do beta reduction, and then that means this x will be replaced by this part. So it will be f of this will be replaced. So it will be lambda x dot f of x. Again this x is lambda x dot f of x x. So this is where if we do CBN, that means what, I have taken this n as it is and I have supplied it in the body of M. X is replaced with this n I have gotten, and we will stop here. CBN says that the argument is passed as it is and then it will stop here. Now suppose we do CBV, then what is going to happen here? So if we do CBV, so there by this beta reduction we are going to get here this f, this part. Now at this stage we are trying to supply something to f, but we cannot give, because here whatever we had here, we got the same thing here. It is the same expression that we had. So we have done it here, we have expanded it once. So here when we do CBV, so then it is trying to evaluate this one. So it says, okay, if I expand it once, I am going to get this. But I have to supply something to f, I cannot do this. So what it will do, it is looking that, okay, whatever I started, I have got back the same thing. So CBV now will evaluate this again. So it will get back another f, then the same expression that we had, we will get back. Again it will apply the same argument, same logic, same reasoning it will apply. So it will go on doing this. So it will be expanding it again and again. So we are going to get infinitely many occurrences of f. That means as if f is never, this f that we had or whatever it could be, we have never used it. F of something, that argument has never been evaluated. So f was never evaluated. So that means that if we want to use y in a CBB setting, it will not work. That is why we said that y combinator has been designed to work in a call by name setting. If we apply it to call by v setting and we think that it is also going, no, it is not going to work. It is because of this. So this motivates us to suggest, okay, let us see whether we can have a combinator for that will work in a call by value setting. So then that is another combinator called a Z combinator. Now let us see how we can obtain the Z combinator from the Y combinator, whether there is any similarity or not. So we study the Y combinator again. So Y combinator is this lambda, we know this lambda f dot f of xx and this. So this is where the recursion obtains. That means it is applied over and over again, that we got that infinitely many times that applied. Now what we have to do? We don't want to do this. That means we don't want to allow these things to happen. So how to do this? So now our motivation comes from, we have studied eta reduction. So our motivation from eta reduction is that eta reduction says that lambda x dot mx, eta reduces, this mx, eta reduces to m, where x does not belong to the free variable of m. Now whenever we have a reduction like m, it could be beta or eta, n is called the contract term of the reduction and m is called the expansion of the reduction. That means m, so we can say it is a contract term or reduction. That means this m is a contract term and this lambda x dot xm, this term is an expansion. So our idea is, from this eta reduction we know that if I do eta reduction I will get. Now we look the reverse way. We look reverse way. That okay, instead of writing m, contract term means it is simpler, smaller. That length will be smaller. Expansion means larger. Length of the formula will be more. So now we go on to reverse way and we say okay, I will work with expansion. Now expansion is what is our starting point. Now if we look at it very carefully, what is the difference between this lambda x dot mx and m? Lambda x dot mx here, m we cannot see m unless an argument x is applied. X is, that means m is not exposed. Unless we apply that argument x, m will not be exposed, and that we studied there. So that means we can say m is wrapped in the expansion, and the term that we have here is a very nice term for us, that is called a wrapper. So the expansion of the eta reduction is a wrapper in the sense that it wraps m in such a way that unless an argument is fed into it, we cannot evaluate m. Now if we substitute this, what is our m here? Our m here is this xx. So we want to do wrapping of this xx. Wrapping of this xx means this expansion term of an eta reduction. So that means this is our xx. So if we wrap it, we are going to get lambda y dot xx of y's. This is that wrap. Now instead of writing this xx, we wrap it and we say we simply have a wrapper of this wrapper of xx. So it is now very easy to see that we have obtained the z combinator from the y combinator by wrapping xx. Idea was that we should not allow xx to be just carry on with the computer, it will not unfold. Only when a parameter of a recursion is passed, this part x, this m will be evaluated. Otherwise, as long as this is not happening, it will be intact. So the eager evaluation that we had earlier, it was a contract. Earlier we are working with the contract term xx. When that was the case, it was eager evaluation. Now it will be like a lazy evaluation, and this is what we want. So now we will see how this will work. So zt now will be as before, it will be this one. So now zt if I do a beta reduction, it will be lambda x of this. So this part, okay, we can write it lambda y dot again this. So now if we do again beta reduction as before, so this x goes away, we have f comes here and we have lambda y, and now we can write it, we can see that this is a bit lengthy term. So we have, so instead of this, let us put it some other symbol. We can write, I can say m, and I will replace x here with this m, and I will write here m. I think m you might get a bit confusing with the original one, so perhaps n will be better. So n I will write here, x will be replaced here with n, again x will be replaced with n, and we have y, and we have this term. So now this is our zt is zt, actually this is t, sorry, this will be t, this will be t, this will be t, this will be t, because we have replaced t. So the t comes out and we have got this lambda y dot nn y. Now nn part y is, what is this nn? Nn part y, it is actually nn part y is actually this part. See, n this is also n, this is n, this is n. So this is actually, this is obtained by zt. So we can write here lambda y, nn is essentially zt, this is zt, this is y. So here you see that zt, that was earlier what we got yt is tyt. Now in call by value we are trying to write y, so we are embedding this wrapping yt. So this is the wrapped version of this, and by eta reduction, so this is equal to, it should be equal to, and this is by eta, we know it will be, this part is t, zt. So zt, then zt is the same as our y, zt is like y. So in essence the evaluation is doing in a lazy evaluation is done. and that one how it will be, then that yt, then this zt, because it is wrapped. So the arguments of the recursion that we want to do will not be evaluated unless you get an argument for y. So thus now if we want to do, recall that we had a function like f of lambda g dot 0 and we are trying to do call by value for a y combinator and we failed. Now if I do f of, if I do z of f, so z of f will give me, z of f will give me f of y zt, f of zt, that means zf. So that means we are going to get lambda y dot zf, lambda y dot zf. I have lambda y dot zf and lambda y dot zf and I have y. So now this is lambda g dot 0 and I have zf of y. ZF is f zt, zt is this one, f zf, it is f zf. F zf in written in this way, f zf is this one, actually we are writing this way, this expansion we are going to write here. So this is zf is f zf. Now here this part there is no argument for y, we do not have any argument for y. So then by beta reduction we are going to get this 0. This is the difference between the evaluation of y combinator in a call by value setting and the z combinator. So z combinator in essence has done the job. So we will see how z combinator is going to work for a simple function. So now we are going to evaluate z combinator to see how z combinator will give us the factorial function, how it will. So factorial 1 is what we are going to do. So we know zt is zt embedded here. So f is equal to, then f is equal to zg, that will be equal to g of, then this one lambda y dot zg of y, then f of 1 then will be equal to g of lambda y dot zg of y, this whole thing with 1. So then that is that we can call it g of this part, we can call it m and we can call it 1. Now the g part is our, we know it is lambda f dot lambda n if n is equal to 0, that is we are testing whether it is 0, then 1, then it is n times f of spread of n and this is m and this is 1, and by beta reduction we are going to get if n times f of spread of n and f is now replaced with m and now we have 1. So by beta reduction we are going to get if 1 equal to 0, 1 times spread of m, spread of 1. Now 1 is equal to 0, this is false. So then this will give us beta reduction, we are going to get 1 times m of 0. This is predecessor of 1 is 0. Now let us evaluate m of 0. So m is equal to lambda y dot zg dot y, then m of 0 will be lambda y zg y 0. Now y will be consumed, so it is zg of 0. Zg of 0, zg of 0, if we want to compute, how are we going to compute again zg of 0? It is g y z sort of a thing, g y z, it will be g y z with 0 here. So this computation we are going to repeat here. So we are going to get this y. So 1 will be, instead of 1 it will be 0. So here it will be true. So 1 instead of this we are going to pass 0 here. So 0 will come. So 0 equal to 0, this will be true. So this part will be true. So then this part is going to return us z0 of 0 will be 1. So then this part will be then become 1 times 1, and that is 1. So factorial 1 we have obtained. So now you see we were saying that this zg was wrapped. It is not allowed to use zg unless we are supplied with an argument. What is that argument? Here the argument is 0. So that means when you are calling the recursion is coming, so it will wait till that recursion value has been supplied. The moment it is supplied, then only it is going to be evaluated. So then now again as before, so we have now come to the point where the argument is 0. So we have evaluated and now we are doing as before like y and we have got the value we want. So this is the idea of evaluation of Z combinator. Where now our goal is to show you some well known recursive functions like addition, multiplication, exponentiation, and all of these recursive functions are defined in terms of some elementary and well known simpler functions like successor function and predicate function, predecessor function. So successor function is defined as, so the it is defined on natural numbers, that is from 0, 1, 2, 3 up to infinity. So successor of 0 for example is 1, successor of 1 is 2. So in general successor of n is n plus 1, and there does not any number such that successor of that will give us 0. So you are always going to get 1, 2 and so on like that. Predecessor function is the reverse, you can think in that way, that predecessor of 0 is always 0 and predecessor of n is the previous number. The predecessor of 1 is 0, predecessor of 2 is 1, but predecessor of 0 is 0. So these functions will be very useful for us. So a simple motivation of successor function would be that lift, when we are using a lift, so we start at say ground floor 0, then we say we want to go to first floor. So we say from 0 we are going to 1, successor of 0 is 1. So then we say from 1 we say we want to go to 2. So then we say again 1. So 2, that means it is a successor of 0. So all of these numbers basically 2, 3 etc. they are all successor of 0, so many times of successor. Now there does not exist ground floor, we do not have anything like something from which the lift can come to floor 0. From any, there is no point where from we can come to ground 0. So because this is our starting point, ground level, lift is going this way and lift is going down. Now lift at this point also when it is going down, so it is a predecessor function from 4 to 3. So predecessor of 4 is 3, predecessor of 3 is 2, but predecessor of 0 the lift cannot go down below 0. So predecessor of 0 is 0. So that is the a simple analogy to understand or keep in mind what is the successor function and predecessor function. It is operation of a lift. The lift, there is a boundary, the limit after which it cannot go down, or you cannot say successor of 0, you can say 0, you cannot say I will leave 0, it will go 1. So 0 always, successor always builds up, predecessor always goes down, but it is not, you cannot go bottom of that. That is the idea behind successor function and predecessor. This will be useful when we define the, say our first function is the addition function. So add x, y, we say if x is 0, that means if you add two numbers, the other one number is 0. Then 0 plus y, so here as if we are doing the add, that 0 plus symbol we are not using here. So we are doing 0 plus y, say, that will give us y. That plus we are writing as add. Now if it is not 0, this is not 0, that means we are saying x plus y I want to do. How I will do? X is not 0. So I am saying okay, I will do x minus 1, that is predecessor of this, and I will do y plus 1. So that is equal to x plus 1, x plus y plus 1 minus 1. So this gets cancelled, so you get this one. So here why this definition is correct, why you might say that why we are writing in this way. So here the person stops when this x is 0. So suppose we start something, that means this x is the recursive. What is it? Recursive is on this one. So if I do a predecessor of x, that means it will reducing it by 1. How long can we go? We can go till it comes to 0. After 0 we cannot reduce it, that point is stopped. So this is the basis of recursion, this is the base case of the recursion, and this is the inductive case. So this definition then is correct, and this is way of defining addition. So we will show how these two lines of our add function will help us write perform add. So add 1, 2. So then this is the second line I have to do. So here x is 1 and y is 2. So I will do add of predecessor of 1 and I will do successor of 2. So add of predecessor of 1 is 0 and s of 2 is 3. Now the first line comes that x is 0. So this will be x is 0 returning y. So I will return 3. So 1 plus 2 is indeed 3. 1 plus 2 is indeed 3. So this is how we have obtained recursion. Now we can write this recursive function another way also. That means in the, so we will have something like add on the left hand side, we will have add on the right hand side. But just now instead of applying the two functions to the two arguments, we say I will do add as before, but I will now apply the successor on the outside. So then what this means is, you are saying x plus y we are doing as x minus 1 plus y, and then successor means we are doing plus 1. So that means this we can write x plus 1, x plus y plus 1 minus 1. So this get cancelled. So this is x plus y equals. So this is another way of writing. So we are going to use this one for our illustrative purpose. You can also do the same thing for the previous one. So now our idea is to write a lambda encoding. Recursion is not provided directly in lambda calculus, we have done for factorial. Now we are going to do the same thing for add. So our strategy will be same. So we will first write add in this way. There are two parameters x and y. So we write lambda x, lambda y. So we are testing this part we are writing. If x is 0, then we are returning y. If that is not the case, we are doing successor of this whole thing, we are writing add of this one, which is recursive. But we have to write a non-recursive function for add. So we write let g is equal to, this is passed as a parameter now. So we lambda add, everything else remains same. But now this is not the add function. So our now combinator knowledge says that add will be represented as yg. So add is yg. That will allow us to do the recursion. So now we are going to see add function and we see how add of 1 2 can be computed. So add of 1 2 is yg. So we know add of 1 2 means yg, but yg is, so that means y, it will be y of g, yg of 1 2. Now yg is g yg, it is gyg, gyg of 1 of 2. Now g is our this part is our g. So we write lambda add lambda x lambda y. If is 0 x then y, otherwise we are going to take s of predecessor of x and y. Now we are going to do first, again we are going to do only yg. So beta reduction is add will be replaced by yg. So we are left with lambda x dot lambda y. If is 0 x y s of yg, this will be pred of x and y. Now we have to pass these two parameters. So we have 1 and then we have 2. So after I pass x, I will get lambda y is 0 1 y s of yg, pred of 1 and y, and then we have 2. Again beta reduction will give us if is 0 1 2 s of yg, pred of 1 and 2. Now is 0 1 is 0, 1 is not 0, so this part is false. So we will get the answer as successor of yg, predecessor 1 is 0 and it will be 2. This is what we have obtained. Now then we have to now compute yg of 0 2. Now yg of 0 2 will be again gyg of 0 2. So this will be, now we have to compute it as gyg of 0 2. This whole thing gyg of 0 2, again we have to do as before. So here we can see yg will be, add will be replaced with yg, and here finally x will be replaced by, here we are going to get is 0 of 0 and 2. That means is 0 0 is now true, and hence the return value, return this value we are going to return as 2. So we are going to get s of 2. S of 2 is equal to 3. That means addition of 1 2, we have got the desired result 3. So this computation proceeded in the same way that we did for factorial function, and the terminated because we have a base case. So pred 1 at some time or the other, eventually we are going to get this is 0 of 0, this term we are going to get, and this is guaranteed by our predecessor. Every step it is reduced by 1, so eventually it will get 0. So this term we are going to evaluate it once, at the point we are going to stop, and then we are going to compute and get the answer. Now we carry on our discussion, and now we go to multiply. Multiply let us define. Now multiply, again we define in a similar way. So multiply m, if you multiply m and 0, m is 0, it will be 0. Now you multiply m and n, that is if m multiplied by n, that we are saying that you are multiplying n time, n you are adding with multiply predecessor of m. Predecessor of m is, this is m minus 1 and n times n. So this will be n plus m times n minus n. So these get cancelled. So we are left with m times n. So left hand side is equal to right hand side, and so the definition is correct. And so here you see we have defined multiplying in terms of addition. Addition is also, earlier we have defined addition in terms of successor. So that means essentially we are doing successor operation we are doing in, but we are not writing successor, it will looking very complicated. To make things very easy, so we are writing it in addition at some higher level. So we have obtained from successor the add function. Now from add we are doing multiplication. So multiplication then essentially it will be, essentially we are going to do predecessor to reduce the value of the argument by 1, and all the time essentially we are doing addition. That means we are doing successor function. So if we want to do, say for example, multiply 2 3, so this will be add of 3 multiply predecessor of 2 3, that will be add of 3 multiply predecessor of 2 is 1 comma 3. So we have to do multiply. Now multiply 2 3 means we have to do first multiply 1 3. Multiply 1 3 then will be add of 3 multiply. Now it will be predecessor of 1 and it will be 3. So it will be add of predecessor of 1 is 0. So this will be mult of 0 3. Now mult of 0 3 is 0. So this part we know it will be evaluating 0, and add of 3 0 we know this will be 3. So that means this part is evaluating to 3. So we have now got there, this will evaluate to. So this part will become add of 3 3. That we know is 6. So multiply 2 times 3 is 6. So this is what we have obtained. So again our task is to show an encoding in lambda calculus. So we take this definition, recursive definition of, and write as it is in lambda calculus. So now again it will be, it is recursive. So we give a non-recursive. So we pass this as a parameter. So we get mult. Now this is non-recursive, but it is not multiply. So we know multiply will be yg. So it will be y mult this and all, which is recursive. Again we can, if you want to do multiply 2 3, again we can do the computation as before, and we will come up with the value 6. Now we have the exponentiation function. So exponentiation means we are doing x to the power of n, where n is any integer greater than or equal to 0. So that means x to the power of 0 is 1. So we are writing x n. If n is 0, then we are going to get 1, and if otherwise it will be x to the power of n, we can write as x multiplied with x to the power of n minus 1. That means multiply. Now we have to do multiplication. So multiplication of x and x to the power of n, that is right, power x minus 1. So now power then uses multiply. That means it is using add. Multiply uses add, uses successor. So again basically we are using successor function in some way. So if we want to do power of 2 2, so again as before we are going to do mult of multiply 2 power of 2, and this will be 1, and we have not written pred, so we do 1. So power of 2 1. Now we have to do power of 2 1. So that means 2 to the power of 2 we are trying to do. So mult of 2, this is power of 2, this is 1 minus 1, that is 0. Now mult of 2, power of 2 0 is 1. So and we know mult of 2 1, that we know as 2. So then this value will be 2. So this will be mult of 2 comma 2, that we know as 4. So 2 to the power of 2 is 4. So we have got the answer. Now as before we will write the encoding. This is quite, now we have understood how to do. So we take this recursive definition, we write the recursive version, take this as a parameter and write g is equal to lambda pow dot this one power of this. Now power is y of g, so it will be the last step. So all of these functions we have shown how they can be encoded. Factorial function, add function, multiply function, exponentiation can be encoded in lambda calculus, very straightforward. Only thing we need is the starting point is a recursive definition. This is the starting point. If we have this, then writing this is quite straightforward. So these functions are this addition, multiplication, exponent, they are called primitive recursive functions. By primitive recursive functions, informally we can say they are built up from some elementary given operation. Say for example, successor function is an elementary function, predecessor is an elementary function. or say identity is an elementary, so 0 function is an elementary function. Now the operations that we can do, they are say composition of a function. So from that successor we can do composition, and we can do recursive functions of n plus 1 RE to n RE. These types of things we can do. So using that we can derive this function. So we have derived the add function using successory function, which successor elementary function. So then add is a primitive, and then using add we have again used composition. So there in add we did composition of add and successor. So then multiply we did add, we have done composition of that and other function. So this way we have proceeded and we have obtained the other functions as well. So they are all called primitive recursive. So the strategy for writing a recursive function in lambda calculus is we start with the recursive definition of a function. That means either it is given to you or you can use it from some of your elementary knowledge, you can build up that function. So assume that it is given. So if the function is f, we are going to include lambda f as a parameter and call it g. Then we say our claim is f will be yg. So f will be, this will be the lambda encoding. So there is a nice theorem given in Barendrecht in the handbook of theoretical computer science, volume B. There it says any recursive function is lambda definable. That means if we know that function is lambda recursive function, then you can always have a lambda encoding for that. So then we can summarize the discussion that we have done in today's lecture. So one, we have discussed some combinators like Turing combinator, the Z combinator, and how they are applicable, how they can be obtained from the other. And then we have studied some recursive functions and how to write encode recursions, and we have shown how to evaluate them. So I believe we will now have the confidence to write recursive functions in lambda calculus. So we stop here, and this is the reference that we have used for our that theorem of Barendrecht. Thank you for your kind attention.